We're gonna continue today, and we're going to look in much more detail at this topic of surds, or which really looking at the square roots or simplifying square roots. Right. As we mentioned earlier, the square root of a number, square root of a, can be written as a fractional power, a to the 1/2. And what does that really mean? If I took, say, something like this, the example, if I said, what is the square root of 25? All of you would tell me 5. And let's look at how we got this. Suppose I put this to the 1/2 power. This is 25, but 25 is 5 squared. So if I now use my rules of indices, my power rule, I would multiply these two things, these powers together, and I would end up getting 5 to the 1st, or simply 5. Yes, a long way it might seem to end up with my answer, but at least you're understanding that this fractional representation of my square root is true. Okay. So what we're going to do is explore a bit what happens with these, or I'll give you some rules and then we will look at them. So if I have square root of a times square root of b, it is the same as root ab. So this is a product rule, and we similarly have what is called a quotient rule or a division rule. Okay. All right. Let's also put in some other things. Suppose I had root a based on rule number 1. We'll have some consequences. If I had root a times itself, this would be the same as root a squared, which is simply a. All right. So either way, or let me also put in another representation of it, which is a. So any of these are ways of getting just a. All right, let's look at rule 1, which is a product rule. And let's actually prove it. As we go through this course, I know we haven't formally spoken about proofs yet, but we'll get to that. Let's see what we would have. So let's prove, I'm going to take it the other way. It doesn't matter, however. Once you've done it one direction, it's going to be the same thing, just reverse. So proof. What we typically do in a proof is we might start with one hand. So if we have prove A equal B, what we can do is what we call a direct proof. Starting from one side, we would move all the steps to get to the statement or expression B, or vice versa. Right? There's another way of proving something. Yes, we want to prove A equal B, but it's a bit difficult to go directly. So instead, what we could do is we could prove that A is equal to C, and likewise B is equal to C, and therefore we can conclude that if A equal to C and B is equal to C, then by something like a substitution, A must be equal to B. Right? So these are the two methods of proofs that we will start out with. There's another method, but we're not going to be focusing on that at this time. So let's start with this. Left-hand side. So some shorthand notation. You'll see this in music also. So left-hand side. The left-hand side of the question is square root of AB. Now, if I convert this to fractional exponents, then I would have ab to the 1/2 power. But again, using my power rule, this is the same as a to the 1/2, b to the 1/2, so power rule of my exponents, I end up, here is nothing more than root a times root b. And what I've come up with, this is just the right hand side. So we have proven, sometimes in your books you'll see this little symbol QED, which means it is shown. So we have shown that the left hand side is indeed equal to the right hand side. All right, let's look at some examples and ideas behind simplifying some square roots. So if I had, so let's look at some terms. Simplify the following. If I have a square root of, say, x to the 8th, this is a nice even power. It is just the same as dividing the power by 2 or taking 1/2 of it. So I end up with x to the 4th. However, suppose I don't have a nice even power. What would I do? And the answer is, well, we could separate our given radicand into two parts. This is a perfect square, and this is sort of the leftover, sort of like the stepchild. Okay. And now using my rule of for the square root, the product rule, the first part, this part can be simplified, and we have the rest is left. So this is x to the 4th times root x. Let me do this with some numbers just to make it a little bit clearer, or hopefully a little bit clearer. All right, if we had, say, the number square root of 27, I could, if you don't know it already, we could do what we call a prime factorization of 27, and we end up with 3 to the 3rd power. Now, we don't want to just change this and say, oh yeah, it is 3 to the 1/2, because of that division by 2. Instead, what I want to do is separate the 3 squared into its highest even power, right? So this is the highest even power that we can get, and then here's my poor little, leftover. All right, okay, what do I do? What do I get? So this would be the square root of 3 squared times the square root of 3. Simplifying, which is why you took out the even power, this was just 3 root 3. Let's look a little bit. Could I do that simpler? Sure. If some of you, let's look, let's talk about this. Let's look at the perfect squares, which are 1 squared, 2 squared, 3 squared. But in particular, I want you to know them. So 1, 4, 9, 16, 25, 36, etc., etc. Right? So these are our perfect squares. I could ask the question, if I have 27, which of the perfect squares go into it? 1 goes into everything. So I really am not going to use 1. But I could look at 27 as 9 times 3. If I now take the square root, breaking up that square root, root 9 times root 3, you end up with exactly what I have above, which is 3 root 3. Why do I want this? Because this is an exact answer. Recall when we talked about numbers in our very first lecture, I believe, we talked about these square roots that are not rational. They're not rational. Hence, as a decimal, they keep going on and on forever. Right? Okay, so let's look at another problem. Another question. So, right, so the idea or key idea behind all of this is take the perfect part, put it to the front. We will be able to simplify that. Whatever is not able to be simplified will be left underneath the bracket. All right, so let's again go back to some algebra expression. Let me see if you get it this time. So if I have something like this, let's take almost all the alphabet. X squared, y to the 7th, z to the 11th. What I'm going to do is look for the highest even number power on each of these variables. And anything that's left over would be here. So I have this product, and hopefully you agree the total power on y would be 6 and 1 is 7. Total power on z is similarly 11, as we started with 10 and 1. Again, I'm exaggerating the powers of 1 on the back end here. All right, so let's take the square root. We have x squared, y to the 6th, z to the 10th, and yz. What do we have from a perfect part? Half of these powers, z to the 5th, and root yz. Okay, so, but let's practice a bit with some numbers right now, and then we go back to joining them together. All right, if I have the square root of 50, again, you could go through and ask what are the perfect numbers that, or perfect squares that go into 50. You would say 25 times 2. If you don't see it, please remember you can always do a little rough work on the side. What's a prime factorization? Right, and so I could say 5 by 10, and then here is a 5 again and 2. So 50 is 2 times 5 square. Of course, I'm going to want the 5 squared to the front when I'm ready to take the square root, because it's the perfect part. Okay? So sometimes if you don't see it right away, then this is an alternative method. All right, but either way we'd end up square root of 20, end up with 25, square root of 25 is 5, and so 5 root 2. What else can we do? Now, suppose we have, in the same way that we have these, we could say, all right, suppose I have 5 root 2 times 3 root 7. I could combine. Here are the whole number parts. Here are the square root parts. If I combine these, I end up with 15. If I combine these, I'll be using the rule root a times root b is the square root of root ab. I only want to have my final answer with one square root sign. So square root of 14. And that's my final answer. Nothing else can be done, etc. Notice if I should have 5 root 2 square, recall where we got this. Okay, so I'm gonna separate my, so recall that root 50 was 5 root 2. So I'm asking the question, what would happen if I square both sides? Already you can see from this I should end up with 50. Right? But let's do it the long way. Let's see if I, here. So this would be 5 squared times root 2 squared. Each term in the bracket is squared. So I get 25 times 2, which is 50. Exactly what we had predicted over here. So sometimes it all depends on what you're given, but typically we want to reduce our radicals or square roots into what we call their lowest forms. Okay, let's do this. Suppose we're given 2 root 3 times, what should we get? 5 root 6. Alright, so as we had done in part F here, so as we've done over here, let's again look at combining the coefficients. So we'd have 2 times 5, and now the root parts, right? So we have 10 root 18, but are we done? We're not done. We always, whenever we are doing these problems, we need to look at what's underneath the square root sign, underneath surds, and determine, is it simplified? And if I look at 18, well, 18 is 9 times 2. So I can definitely rewrite that square root, 9 by 2. This is square root of 9, square root of 2, and I'll just be bringing back this 10. What do I get? 10 by 3 root 2, which is 30 root 2. Okay. All right. Now anything that we get, what you've seen here, we are multiplying and or simplifying a term. Now we can add, subtract, multiply, and as I gave you earlier, the division rule. But let's look at a sum. So let's look at part I. I'm given the square root of 12 plus the square root of 3. Don't just look at that and say, oh, these are unlike terms, and hence there's no further that I can go. Look carefully, and if you do, you'll notice that here, this is not simplified. So what your first job will be to simplify it. And how do we do that? Well, square root of 12 is 4 times 3. It's the square root of 4 times 3, and so that part can be simplified. In going through using a product rule, so I'm using root AB is root A times root B, then I end up with 2 root 3. Square root of 4 is 2. Alright, now what you see here, and you'll get much more comfortable with it as you go on, is that if I factored root 3, you would really end up getting 3 root 3. Now what we can say is that these are what we call like roots or radicals, right? They're the same terms underneath the radical sign or in the radicand. And so we can add the coefficients. Right? So as an aside, let's compare. What I'm saying is if I had 2x plus x, there'd be no hesitation you would have ended up with 3x, because these are like terms. Each had the same variable. How did you get that? You've done it so long ago that you have forgotten. If I am to factor the x, then what you did was you looked at the coefficients and you simply add them, right? So once I've identified like terms, the idea is just add those coefficients. Okay. And get your final answer. All right. Let's look at another one and see what we would come up with. All right. Let's make it a bit longer this time. THI, so we'll call this J. And I'll hide everything so that we can see how well you understood your textbook. And this is just backing it up. Or maybe I'm doing the opposite. All right. So let's look at 45. It is 9 by 5. If I come back, here I have root 20. Root 20 is 4 times 5. And the others, everything else doesn't need any simplification. When I look at this, square root of 9, square root of 5, 3, square root of 4, square root of 5. Since I have more room, I seem to want to show you all the steps. So 3 root 5, 3 and times 2 root 5, 8 root 5. Let's keep simplifying. All these are like terms again. So hopefully from the last thing, you remember, I can just look at the coefficients. I'm adding 3 and 6 and subtracting 8. 9 minus 8 is just 1. You don't, as in when you were doing x's, so we didn't write, you wrote x, not 1x. So when the coefficient is positive 1, well, when the coefficient is 1, we don't really show what's going on. Okay. All right, let's look at the next one. Oops, change my color here. And let's say that I have 3 root 28 minus 5 root 63 plus 3 root 50. Okay, take a moment and try to do this. If you are watching this on tape, then do pause it and we'll continue. Okay, so let's start back. 28 is 4 times 7. 63. 63 is 9. 9 times 7. And 50 is 25 times 2. Okay. Let's simplify each of these. I'll use a bracket. Square root of 4 is 2 root 7. Next term will give me 3 root 7. Next term will give me 5 root 2. And again, I go through, I multiply the whole number parts. And we have 6 root 7, 5 3s, 15, I should say integer parts, not necessarily whole number parts, plus 15 root 2. And now when we look at this, the only like terms are these two with the root 7. Root 2 is an unlike term. So again, if I compare to using my usual, say, x's and y's, this is what I would have. I know that I could combine these, right, and I'd end up with negative 9x and 15y. So in a similar fashion, I look at the coefficient, 6 minus 15, it is negative 9. So negative 9 of root 7 and 15 of root 2 are left. So that's my final answer. Okay. So this is how we add and subtract when we are simplifying our roots. Okay, what else can we do? So we're going to dedicate quite a bit of this time to let's start out simple. Let's look at 3 root 2 plus 5. Okay, so this is just a distributive property, and so I would have root 2 times 3 root 2 plus root 2 times 5. Okay, let's combine. So multiplying 3 and root 2 squared. All this product that we have, we typically put the whole number or the integer to the front and the radical behind. So 5 root 2. Now we're not done. Do you recall what happens here? What is the rule? So the rule that we're using is that root a all squared is simply a. One is the inverse of the other. So we end up with 3 times 2, 5 root 2, or 6, plus 5 root 2. Doesn't matter. Let's do some with the minus sign. Okay. All right. Again, distribute. So 7 root 3 times root 2 and 7 root 3 times 2 root 3. Okay. When we combine these, root 3 times root 2, and here we can write this as 7 times 2 times root 3 squared, or root 3 times, let's write it out the other way, as it's given, root 3 times root 3. Alright, so 7, what do we get here? We combine these. What rule am I using? So I'm using root a times root b is equal to root ab, and for the next part I'm using that root a times itself is equal to a. So we end up with 7 root 6 minus 14 times 3, so 7 root 6. 14 times 3 would be 42, and this would be my final answer. Okay. All right, now anything that we could do with our binomials, so I've done the distributive property, I can do with these surds. So let's continue. Right. Again, hopefully, if you're getting tired, just pause this as we practice. And so let's say that I have 2 plus root 3 and 3 minus 5 root 3. Same way that you learned the FOIL method, that's exactly what we are going to use here. And so we have 2 times 3 plus 2 times negative 5 root 3, root 3 times 3, and root 3 times negative 5 root 3. Alright, so I'm just observing the signs of each term. Alright, so our first product is 6. Our next is minus 10 root 3. Our next, I'm just going to reorder them. So 3 root 3. And our next will be negative 5. Let's work this one out. Root 3 times root 3. What do I get there? That's just simply 3. So, our expression, I'll wait and combine these in a bit, becomes 3 times 5, which is minus 15. I can rearrange. So, rearrange, regroup. I end up with 6 minus 15 and minus 10 root 3 plus 3 root 3. Here we have like terms and here we have like terms. So 6 minus 15 would be negative 9, and minus 10 plus 3 would be minus 7 root 3. Let's see how good you are. In less than 2 minutes, in less than a minute, tell me what this answer is. Aha, I heard my first answer. Okay, so what we have here is the difference of, well, we have the product of conjugates. Right? And so that leads to the difference of 2 squares, root 2 all squared minus root 3 all squared. But this is just 2 minus 3, which is negative 1. Okay. All right. We haven't done one thing yet. So we've looked on simplifying, we've looked at multiplication, we haven't looked at divisions. Alright. Now, if we had something like, what is the square root of 4/9, then not a problem. I could use the division rule, which tells us to, let me just state it again. If I have the division root a over b, you will simply take the fraction of the square root of a over the square root of b, and in this case we ended up with 2/3. So the square root of 4/9 is 2/3. Of course we could check our answer and we would see if we squared the result, right, we would have ended up with exactly what was under the radical sign, which is 4/9. All right. Now, again, this is all well and good, but suppose instead we had, say, a square root of 1/2. So no problem here, square root of 1, square root of 2. Numerator can be simplified. Presently you'd think that we are done, but we're not. Alright, we are not simplified until there should be no radicals in a denominator. Now you might wonder why is that? Well, let's just go back a little bit to division of decimals. If I had given you, so I'm answering the question, by not answering the question directly. So if I had given you 1 divided by, say, 0.02, how would you simplify this? And many of you would tell me that, well, you can't divide by a decimal, so you'd have to multiply the denominator by 100, but if you did that, you'd also have to do the same to the numerator, and we would end up getting an answer. We'd end up being able to divide this, or we end up getting a fraction that was, if it were some other number, we'd end up getting something that was not reducible, etc. All right. Now, what about the square root of 2? Square root of 2, 1.414, but it changes. This is irrational. So if I should have 1 over root 2, then it is over this number that goes on and on forever. I can't, there is no end. I don't know how far I need to go down, or rather, there is no end, so I can't go all the way down. I won't know how to leave my answer to, say, 7 decimal places, depending if I need that level of preciseness, etc. All right. So let's look at how do we deal with this idea of not leaving radicals in a denominator. How can I, alternately, or find an alternate answer? And the method is what we call rationalizing the denominator. So I'll come back to the problem in a bit. So let's look at the steps. Suppose you are given, or you have at the time, root A over root B. I can choose to multiply. So if the denominator has a square root, I will multiply by 1, but I'm going to choose my 1 in a particular way. I'm going to choose that whatever is on the denominator, in this case root B, I'm going to multiply by that. And so what I end up with is root A times root B. I don't really care about the numerator. I know how to simplify those. But in the denominator, square root of B all squared, what is that? That's simply B. So I have obtained something without, there is no radical, no surd in the denominator. Right. So in words, what we're going to do is multiply both numerator and denominator by the square root that is in the denominator. Right, hence its name as to rationalizing the denominator. So going back to our problem, we had 1 over root 2. What I will do, I am going to choose to multiply this by root 2 over itself. And now taking the numerators, I'm multiplying fraction multiplication, multiplying the numerators, multiplying the denominators. My final answer is root 2 over 2. Now, is this any better than what I claimed that we had up here? Here, when we look at it, 1 over root 2, there was no end. If I should look at the approximation now, so if I approximate this, it'll be 1.414, 2 goes on and on and on. I can divide, this is a nice whole number, so I can divide to any number of decimal places that I want. And so I have resolved that problem of having an irrational number on the denominator. Okay. All right, so let's practice a few and see what happens. So let's practice division. Okay. So suppose I have 6 over root 2. So let's start again numbering. I would write 6 root 2 and root 2 times root 2. Numerator is 6 root 2, so I am combining these and I'm combining those. Over root 2 all squared, but root 2 all squared is 2. We're not done yet. Remember to simplify. Want my answer in the lowest term. So I will go through 2 into itself is 1, 2 into 6 is 3. So my final answer is 3 root 2. Please do not note, and note well, 6 root 2 over 2. I cannot and I should not do that. It's not equal to 6. You cannot go underneath the root sign. In fact, your order of operations tell you that you can only reduce the fraction, the whole number or the integer part. Okay, so please, I don't want to see that on your papers. Okay. Take a few more. If instead I have, I'm starting out a little easy here, 4 over root 8, what you can do first is simplify the square root on the denominator. So this is 4 times 2 is 8, so I would have 4 over 2 root 2. You can even go ahead again. 2 can divide this, so I have simplified as much as possible the given term, but I need to now rationalize it. Right, so I need to rationalize that denominator. How do I do that again? Well, 2 over root 2 is the same. I'm going to multiply by root 2 over itself. There's another way, but I won't. This is your first time. So I end up getting a final answer of just root 2. Suppose we have 2 root 3 over root 6. Let's look at this in 2 ways. So, rationalizing the denominator, I would multiply both numerator and denominator by root 6. So I'd end up in the denominator with 6, while 2 root 3 times root 6. Let's combine this part. This is 2, 3 times 6. 2 root 18 over 6. Alright, let's take the opportunity to reduce these. Could have done it any time before. And let's continue. Although we have rationalized the denominator, it is not in its reduced form. We need to simplify the 18. You will notice 18 is 9 by 2. And so continuing, square root of 9 times the square root of 2 over 3. What do I get? I end up with 3 root 2 over 3. Similarly, the answer is root 2. Now the question is, could I have, and each time I ask that question, I know that you're saying yes, by now you've gotten the idea. Could I do this in another way? And let's look at that other way then. So let's examine this part. Do you remember your rules? So I'm going to point out, if I use the rule that root A over root B is one common square root, right? So let's look at what we get here. So this could be written as 2 over and 2 times 3 over 6. If I reduce, I end up reduce what's inside. I end up with square root of a half. So I have 2 times square root of a half. What is square root of a half? Let me just go this way so that I save some room. 2 times root 1 over root 2, which is just 2 times 1 over root 2. Alright, and yes, either you could rationalize and then simplify. I'm also going to look at this a little bit differently. So looking at this numerator, comparing it to the denominator, you might also say that 2, so I'm looking at the rule that A is equal to root A squared. So I'm looking at that rule here. And so I could write this as root 2 all squared over root 2, and this becomes just root 2. So either way, you'd end up with the same thing, whatever is most comfortable for you. But be aware that many times, or sometimes at least, you and your friend could be given a problem and you use different techniques, but you should end up with the same value. Alright, so in the case when we had a single root on the denominator, we've looked at this idea of rationalizing and hence multiplying by whatever root was there. As we saw, there we did it, here we did it, okay, and earlier, right? So we did it in all those cases. It doesn't matter. So if you had, see, that was C, let's look at part D. It doesn't matter if I have, say, 5 over 2 root 3, and I am rationalizing. This would be 5, 2 root 3. You don't need to write the whole term, the entire denominator. You just need the square root of 3, because that's the part I need to get rid of. So numerator is 5 root 3, denominator is 2 times root 3 squared. But root 3 squared, this is nothing more than 3. So I will end up with 5 root 3, oops, 5 root 3 over 2 times 3, 5 root 3 over 6. Okay, so it's still an irrational number, but at least now there is no root on the denominator. Okay, let's quickly look at something. Suppose we had 3 over, say, 2 minus root 3. Okay, this time we have a binomial on the denominator. We can't have a square root on the denominator, so how do we rationalize this? So again, this idea of rationalizing, but we have a binomial. 2 terms on the denominator. So if we have something of this form, I don't care if it is one square root or 2 square roots on the denominator, really don't care what's in the numerator. Then what we're going to do is we are going to multiply numerator and denominator. Oops. gonna multiply numerator and denominator by the same term, and that same term is the conjugate. Right? So on the denominator, I'm going to multiply these are the conjugates. Recall that for your denominator here, this is nothing more than the difference of two squares. So at least that denominator will now look like root b all squared minus root c all squared, or simply focusing on the denominator, b minus c. There is no square root. Just rewriting what's on the numerator, and I just put it back. Whether it needs to be expanded or not, you can decide as you go along. Right, so let's actually look at a question that has one of these things. Did I start out? Yes, I gave you one. 3 and 2 minus root 3. All right. All right, so we are given this and we want to rationalize it. So we would write the same thing back. And now we look for the conjugate. The conjugate of 2 minus root 3 would be 2 plus root 3. We put that on both the numerator and denominator. The denominator is your difference of two squares, so numerator is just be multiplied. I won't expand that yet until I see what's coming out from a denominator. Difference of two squares, right? You would have 2 squared minus root 3 squared, which is, it's just since I've written it over there, 4 minus 3, this turns out to be 1, so I end up with 3, 2 plus root 3. If I expand that, I end up with 6 plus 3 root 3. It might be interesting for you to put this on your calculator and look at the approximation that you get, and you will notice that if you take this side also, so if I take both the left and right hand side and independently look at them on the calculator, you'll see that the approximation is exactly the same for both, even though they look drastically different. Okay. Right, so the idea again, always when you have a square root in the denominator, you want to rationalize, right? And if that denominator turns out to be a binomial, then you have to rationalize using the conjugate. If the denominator turns out to be just a single term, then all you're doing is multiplying by the radical that was present. Oops. Let's go on to part F. Okay. So let's really push you now. Suppose I have, and I'm using, let's not use, you're probably sick and tired of 2's and 3's. Let's do, say, root 5 minus root 3 and root 5 plus root 3. Okay, so again we have to rationalize. Root 5 minus root 3, root 5 plus root 3. I observe the denominator. I'm going to rationalize using the conjugate, which is root 5 minus root 3. I don't know, let's see if you recognize some things here. Denominator is the difference of two squares. So yes, I would have root 5 all squared minus root 3 all squared. Simply, this is 5 minus 3, which is 2. I just wanted to save some space by doing that out. But I don't know if you recognize that numerator is really just the same thing. It's a perfect square. Right? It's a perfect square. And so this is root 5 minus root 3 all squared. So I'm really testing if you remember your patterns. So my numerator would be first term squared minus 2 times that mixed product plus the last term squared, and that was all over 2. Let's simplify. So I get 5 minus 2 root 15 plus 3 all over 2. I end up with combined like terms in the numerator. 5 plus 3 is 8 minus 2 root 15. Okay, you're not done. Look at the numerator. You recognize that they're all even numbers. I could factor out one copy of 2, and we would factor the numerator. Denominators, they cancel, factor of 2, the HCF. And so my final answer is 4 minus root 15. Okay. So sometimes we may have to bring in other techniques, not just the difference of 2 squares, but look around and see exactly what's going on. All right, last question on this. And let's do, say, 3 minus 2 root 2 root 2 plus root 3. All right, so here's what we have. Let's rewrite it again. Oops, root 2 and root 2 plus root 3. We're going to multiply by the conjugate, which will be root 2, root 2 minus root 3. Okay. Let's look at our product. So again, never fails, the denominator is the difference of 2 squares. Let's see what that is. Root 2 all squared minus root 3 all squared. We end up with 2 minus 3, which is simply minus 1. Okay. All right, so the denominator is all set. Numerator. Well, it's not perfect, so this time we will have to use the FOIL method. And in using the FOIL method, we have 3 times root 2, so the first term, 3 root 3, outer, inner was 2 root 2 times root 2, and the last term was plus, it's not crashing there, was minus and minus is a plus, so 2 root 2 times root 3. So let's simplify that numerator. 3 root 2 minus 3 root 3. Okay, and now if we look at these, what do we end up with here? This is nothing more than 2. So 2 times 2 is 4. So this outer term is 4. And the last term, again, if we simplify here, root 2 times root 3, we are just going to combine these terms under one root, and we end up with plus 2 root 6. everything has a negative sign, so either you can write negative, and there are no like terms in the numerator. Oops, 3 minus 4. Or later on we can distribute that negative sign, and so we could write our final answer minus 3 root 2, 3 root 3, and plus 4 if you want, minus 2 root 6. Okay, sometimes you might want to put things in order, so we like to have the nice integer part first, or rational part first, and then we will sometimes order this using the radicals as they are increasing. So root 2 comes before root 3, and we also would have root 6 coming after root 3. But no big deal, as long as all the terms are there, that's all we want. Alright, so hopefully this was helpful, and we will see you for the next lesson.